Hello guys, welcome back to my channel. In this video, I would show you how to design a transformer-less power supply. In my previous video, I showed you how to design a AC to DC converter power linear power supply using a transformer and rectifier, bridge rectifier. Now in this design, I would not use the transformer, but instead I would use capacitor that is probably used at the input of the AC side, and we would use the bridge rectifier, and and the circuit would be very simple. Let's start and see how it is going to design. New schematics. Okay, now place first of all the diodes. Right click, pick new diodes. Okay, again, as you remember that there is no 1N4007 library, so I would use a spice directive, and just as last time I showed you, dot include the path name of the subfolder of the LTSpice where it is present in your computer, and type 1N4007.lib, because the library file extension, and that is the spice model, is in the form of .lib. Okay, so I have used the same. I will show you here. This is the path. This is the path, and this is the file 1N4007. Let's try to open this and see what it is. This is the model, okay, of the diode 1N4007. So we would use this name that is written between dot model and D. This blue line is very critical, so just use exactly this name of the diode, D1N4007. I would simply copy this and right click on control plus right click on this and change the value to D1N4007. Click OK, and that's it. Now copy this same for four diode bridge. Connect them together. Okay, this directive would automatically pick the spice model from your path and insert here in this diodes. Okay, now control plus R to rotate. Okay, so now place the voltage source, AC voltage source. Right click, advanced, sign. Amplitude is always 310 volt for the AC. As we all know, for 230 volt AC RMS, the equivalent peak voltage is amplitude is 310 volt and frequency 50 hertz. Now wire this up. No, not wire this up. So we here are going to use a capacitor, which is a special type of capacitor used in the AC circuits. Okay, and I would take this to be 1 microfarad and 400 volts capacitor, and this resistor I would use here in parallel with this capacitor, that I would take 1 mega ohm, 1 watt. Okay. Uh, okay, so this capacitor C1 is actually the main capacitor. This is the main component of the entire transformerless power supply. This capacitor gets charged in the AC voltage, and it discharges through this resistor. When the AC supply is turned off, the capacitor would discharge itself from this R1 resistor. So this capacitor actually provides a 50 milliampere current per microfarad capacitance. That is, if I increase this capacitor to 2 microfarad, then the output current for the load would be no less than 100 milliampere. If I increase this to 3 microampere, it would be 150 milliampere. Okay, not greater than 150 milliampere. So to be on a safe side, let's take a 1 microfarad capacitor, because we are going to use a LED, a simple LED as our load. And LED actually takes a 25 milliampere to 35 milliampere current for high brightness. So that would be perfectly fine. This 1 microfarad capacitor would be fine. Now this return path would not be connected directly, although it would be connected through a series resistor. This series resistor is also very important because it limits the current flow. This is a current limiting resistor and is actually taken as 100 ohm and 1 watt. This is because why we use this capacitor, why we use this resistor when we have a capacitor as a current limiter. So the answer to this question is that this resistor would act as a current limit resistor for this capacitor, because the capacitor, as we know, at time t is equal to 0, it acts as a short circuit. So when the capacitor behaves as a short circuit, this resistance would also become short. So a very high current flow would flow from these diodes and returns back to this resistor. So this resistor actually prevents the critical DC component, LED or any other DC small DC voltage loads to be, it protects it from damaging. So this resistor is important for this capacitor because it behaves as a short circuit at time t is equal to 0 when the switch is on, when AC switch is on. Although we can use here an NTC, negative temperature coefficient resistor, that would be much better as compared to this fixed resistor, because an NTC would have a certain resistance at a room temperature, and as the current flows through this, the resistance suddenly increases with the increase in current, and as the current reduces, the resistance also comes back to its normal 25 degree centigrade resistance. So I would not go into the detail of NTC, so let's just place this here. Now we are going to connect our load, and yes, we are first going to place a polar capacitor, because this capacitor would act as a filter, for the load. And we are also going to use a Zener diode. Why? Because as we know that the voltage is 310 volt appearing here, and when rectified, the voltage would not decrease to a certain voltage limits that we want for our LED or LED string. So we are going to use a Zener diode. The Zener diode would regulate the voltage to its Zener voltage. Right click, pick new diode. Now here we select type, and we simply go into the Zener section. Short key, as you can see, short key, switching and Zener here. I would select a 15 volt Zener. Okay, let's select a 15 volt Zener diode. So this 15 volt Zener diode would limit the voltage from exceeding above 15 volt. Alright, and this resistor is the Zener regulator resistor. That can be a 220 ohm resistor. And this capacitor, as I said, is the filter capacitor for filtering the ripple voltages, and it can be a 470 microfarad capacitor at 100 volt rated. The larger the capacitor value, the better it is for the filter, for filtering the ripple. Now wire up the components. Okay, now we are going to place an LED. In the LED, I would select a 30 milliampere LED. This LED would be okay. 30 milliampere LED average current and 5 volt breakdown voltage. Now as you see, the symbol has changed its shape. It becomes an LED instead of diode. Now let's place this LED here and our resistor here. This resistor is of course the current limiting resistor for the LED, and let's take it to be 1 kilo ohm, because at 1 kilo ohm and 15 volt the current would be reasonably low for this LED. Okay, so now the circuit is complete. Now we have to place ground. Yes, ground connection, because without ground the simulator will give error. Now let's see what happens when we hit the simulation button. Yes, we are going to perform a transient simulation for 100 millisecond. Let's say 100 millisecond. Okay, I would place a here node, output node, so it would be easy to analyze the circuit. Simulate again. Here, this is the voltage. As we can see, the voltage starts to increase from 0 millisecond up till 100 millisecond. This is because this response we are seeing here, because this capacitor is going to charge. This is charging up capacitor. So we have to increase the transient from 100 millisecond to 1000 millisecond, let's say. Now let's simulate again. Yes, now as you can see, the voltage started to rise up till the 161 millisecond, and it becomes stable at 15.6 volt. As you can see, 15.6 volt has been stable voltage output of this transformerless power supply. Alright, now we would check the load current now, the current through this diode. Okay, so this blue color line is the diode current. Left click on this and we would see the 12 milliampere. The current is 12.43 milliamperes. Okay, so this is reasonably very low current. The reason why this current is very low, not very low but a reasonably low current at 15 volt and 15.59 volt and 12.4 milliampere. This is because of this resistor, because we have used this such a high resistance value in order to protect our circuit from being damaged, in order to protect from this circuit, this LED, in order to protect this LED from being damaged, we use this resistance to protect a surge current, inrush current during the capacitor charge up. So there is a remedy for this. The solution for this is to use a transistor, a shunt transistor. We are going to use an NPN transistor, an NPN power transistor. whose rating would be 400 volt. Obviously the current and the voltage is 310 volt DC here. So a 400 volt collector to emitter voltage breakdown would be sufficient for shunting this output when the output tries to increase the diode voltage. Now how this would work, I think you guys have understood this section up till here. Now I'm going to change the circuit a little bit. Hmm. 2.2 kilo ohm and 2 watt resistor I would use here. And a BJT would be placed here, right, and a Zener diode would be placed here. Yes. And a 1 kilo ohm resistor would be used as a passing resistor for this BJT, power BJT NPN transistor. We can take it as 1 kilo ohm. The voltage does not matter because it is the base current. Base current is always low. So 1 kilo ohm resistor and 2.2 kilo ohm resistor, 2 watt with this Zener diode. Now what happens with this circuit? Actually whenever the voltage at the output of the rectifier tries to increase the Zener diode voltage, then this transistor would shunt the voltage at the output to the emitter to the ground, thus protecting the LED at the output. And as soon as the voltage shunts to 0, the Zener would stop working, and hence the transistor would again becomes open, and this loop will continue until the voltage at the output becomes stable, DC stable, equal to the Zener voltage of this Zener diode. Okay, so let us select the model of this NPN transistor. A 400 volt transistor we need, power transistor, ECEO. Okay, so we have a 150 volt resistor maximum, 150 volt NPN transistor maximum. So we need to download the model from internet. Okay, so to download the model from the internet, there are many options. As you know that there are various semiconductor manufacturing companies like Texas Instrument, onsemi, Vishay, and Analog Devices, and of course Linear Technology. They provide the SPICE models for different semiconductor devices like transistors, diodes, MOSFETs. So we would search first of all the digi key. The digi key would tell us the exact part number of the transistor, NPN BJT transistor, whose VCEO is 400 volt maximum and the current we would use 1.5 maximum collector current maximum equals to 1.5 ampere, and VCEO 400 volt, right? This is the specification of the transistor we are going to search in DG key. Whatever the part number comes, we would go into the manufacturer website and search for the SPICE model. So let's start. Here's the DG key. So I simply write NPN search. Okay, this option 11,800 transistors. Okay, I go into active in stock and collector current maximum I select 1.5 ampere, and VCE, actually this is the breakdown voltage maximum. This is the parameter we are going to select, not this. This is the VCE saturation. This is something different, and this is the breakdown voltage. So we are going to select a breakdown voltage maximum of 400 volt, right? Only 9. Okay, there are only 9 options available. So I already searched this ST13003, but I could not find the SPICE model on ST Microelectronics. They do not usually provide the SPICE models, literally. So I'm going to check the onsemi. This part is also not very expensive and is available in stock. So we are going to select this and check onsemi.com. We simply copy the transistor model from here to their search. Press enter. Click this first option, and now here, as you can see, there are many different things available: product overview, datasheet, application notes, and here is the SPICE model, SPICE model. This is useful for us. Just click on this, and here just click on this SPICE model, and here. So this has been downloaded, this model has been downloaded, and you can see this is .lib model. So we are going to open this model, downloads, all files, this. Okay, so this is the SPICE model of the transistor that is suitable for our application. Simply copy this model, copy, and we are going to paste this model into the SPICE directive as it is. Paste. Okay, so in LTSpice it is very good that you can place the SPICE model in the SPICE directive anywhere on the schematic. Just put this model on the schematic and the model would run automatically. Now right click on this and copy this thing, this FJE. This is the critical part number. This is the part number that you have to use exactly for this transistor. Control plus right click, double click on this NPN, Control V, paste, click OK. Now this LTSpice simulation software would understand that this transistor model is going to use this model, this specific model. Okay, now there would be no error hopefully, and we are going to simulate this again. Okay, now yes, of course we can reduce this resistance to 5 ohm only, 2 watt. Now let's see what happens. And yes, of course, as we said that this capacitor is limiting the current flow from the load to 50 milliampere. So I would increase it to 2.2 microfarad and resimulate again. Okay. Okay, now this 1 kilo ohm resistor is also very high. So let it be 500 ohms. Right. Yes. Now as you can see that the current has been increased to 33 to 30 30 milliampere, and the ripple is 1 milliampere. Ripple current is 1 milliampere, 29 milliampere low and 30 milliampere high. 1 milliampere ripple and 30 milliampere load current. So 30 milliampere current is well enough for this LED, which is also a 30 milliampere average forward current. So just to elaborate a little bit about this capacitor, which is the um, load current setting capacitor, load current setting capacitor. This actually works like this. The capacitance has the reactance at AC voltages. So this is equal to Xc is equal to 1 upon 2 pi Cf, where F is equal to 50 Hertz and C equals to 1 microfarad. Okay, so if we put these values into this formula, we would get Xc equals 2 pi F into 1 micro 3183. I am actually using my scientific calculator for this calculation. So this is 3183 ohms. Now at AC equals to 230 volt RMS, it actually equals to 310 volt DC. This is because 1.414, that is root 2 times of the 230 volt AC RMS. So the current would be 310 divided by 3183, and that is 97 milliampere. This is when we would use 0 ohm resistor here. Although yes, of course, when we increase the resistance to, let's say, 100 ohm, then total impedance would be 3183. This is the resistance, this is the reactance due to capacitor plus the resistor, that is 100 ohm. So that would be 3183 plus 313,283 actually. Yes. Then the current would be 94 milliampere. Yes, and that would be when this resistance, this current limiting resistance, is considered to be equal to 1 ohm. Here, as we can see that the current, as soon as we shorted the series current limiting resistor for the diode, the current has reached to 160 milliampere. That is very much greater than the 94 milliampere. So this means that this is not a good idea to use the diode directly with the load. You have to put a series resistor somewhat, like 10 ohms. So now as you can see, the current is about 140 milliampere, that is 130 milliampere. It is still too high. So yes, our series resistance was right 500 ohm was perfect. And as we simulate again, the current is within the limits of 330 milliampere. So I'm trying to tell that this circuit can deliver a current up to 140 milliampere, but we are not going to use such a high current because this is a single LED. If we are going to use LED, series of LEDs like LEDs in series, and connect them together, that would become a LED string. In many commercial applications, you have seen high brightness LEDs and high brightness LED lamps for different ceremonies. So they usually the customers usually try to use a transformerless power supply because transformers are very bulky and cannot be used with these light emitting diodes. So this is a very handy circuit, and it can be fabricated on a PCB on a very small form factor very easily. But obviously the wattage of the resistors should be taken into consideration, that is 2 watt, this is 2 watt, and other things should be considered. This is the power transistor. A normal transistor would not work here. Power transistor would shunt the voltage. And this capacitor is also a 470 microfarad capacitor. 1000 microfarad capacitor would also be a great idea, but 25 volt, because as we increase the capacitance, the voltage should be decreased in order to keep the size of the capacitor equal, because at 1000 microfarad and 100 volt a capacitor would be very big. So 25 volt capacitor would be fine. 1000 microfarad. Let's simulate and check again. As you can see, now the ripple has been reduced, right? So this is the transformerless power supply. I hope you guys learned something about this, and if you like my videos, please like and share and subscribe to my channel. Thank you very much, guys.